Welcome. There is another important problem. In fact, part of the homework. I left the part of the homework problem related to tetrahedron because it is simple geometry and Coulomb's law. So I'm considering some other problem. The problem says in free space, that means perhaps gravity is absent in a circle of radius r naught at the vertices of the inscribed square. Okay, I've drawn a picture for it. There are 4 point masses of mass m. Two of them carry charges plus q, okay, and other two minus q. You can see them. At the initial moment, these point masses are given the same velocities but directed tangentially to the circles clockwise. No directions are given. It is known that the minimum distance achieved in the process of movement from any of the point masses to the center O of the initial circle is equal to R0. The circle is shrinking. R1 is less than R0. Consider that at any moment of time, the charges are located at the vertices of a square centered at OS. Consider that any moment of time the charges are located at the vertices of a square centered at O. Okay. The action of gravitational forces can be neglected. Of course, determine the trajectories of point masses, determine the time period of motion of point masses. So I have drawn a picture for this. Just let's take a look at the picture. A good look at the picture. Many things are drawn, but I'm going to explain. First, the inscribed square you can see, and due to symmetry, all point masses will move along the same trajectories. So that means remaining at each moment of time on a circle of some variable radius RT. Let's say it RT, variable radius, at the vertices of a square, and a square side can be given as root 2 RT. So now let's look at one of the points that is here. It is affected by the forces F1 and F2, both attractive, and F3 from the other particle, that is plus Q1 plus Q. And according to the Coulomb's law, the magnitude of these forces are let me calculate. F1 will be equal to F2. F1 and F2 will be same, and their values can be written as 1 upon 4 pi epsilon naught q square, that charges are same, divided by root 2r square, that is 2r square. And in the similar manner, F3 can be given by 1 upon 4 pi epsilon naught as q square, divided by the distance between them is 2r, so you should write here 4r square. And the resultant of all these forces, F1, F2 and F3, is always directed towards the center. Otherwise, the motion can't be confined on a triangle. And this resultant force can be written as these two forces. Their F1 and F2 resultant will be in this direction, and we can subtract a minus sign here. So F1 and F2 components, we need to take these two angles are 45 degree. That means That means, yeah. So the resultant force you can write here is 1 upon 4 pi epsilon naught, and why not take it common? That will be that I calculated somewhere, so I can write it. You can also find it, and that came out something like q square upon r square 2 root 2 minus 1 upon 4. I calculated somewhere, and anybody can calculate this thing because there is nothing but addition. So I was just solving this problem, and from here it follows that each of the points moves as if from the center it was attracted by a charge that is opposite in sign and equal in magnitude q equals q under root 2 root 2 minus 1 upon 4. So, and after this comparison, if we move further, uh, here the formula for this FR thing is like Coulomb's law or the law of universal gravitation, that this FR is proportional to 1 upon r square like things. Therefore, the trajectories of the particles are ellipses with major axis. If you have the idea, you can write it r0 plus r1, and point O is one of the foci of these ellipses. So the characteristic time is the period t of an elliptical orbit, and it can be found from the Kepler's third law. And let us find the time period t naught of a point mass m moving under the force Fr along a circular orbit of radius r naught. So this time period can be written as t naught equals 2 pi r naught by v naught being its speed, and you can write another equation, Newton's laws of motion, that is Fr equals mv naught square by r, and Fr is given here. You should write it clearly that Fr is 1 upon 4 pi epsilon naught q square upon r square 2 root 2 minus 1 by 4. Yeah. And try to find out the values of v naught from here. So you can get v naught equals, try to find out. I have just found out, so I'm not going to do it again and again. 1 upon 4 pi epsilon naught 2 root 2 minus 1 by 4 mr naught. You will get the value of v naught, I'm sure. And such a speed must be imparted to the point masses so they can move along a circle of radius r naught. Yes. And when they are moving in a circle of radius r naught, their time period can be written as t naught, and t naught is simply 2 pi r naught by v naught, and you can put the value of v naught here, and you will get ultimately t naught equals 2 pi upon q 4 pi epsilon naught 4m r naught cube by 2 root 2 minus 1. So now you can use the Kepler's third law, and you should write it like the required time period divided by the time period, a square of the time periods equal to r naught plus r1, semi length of semi major axis, divided by 2r naught cube. And then you can get the value of t, the required time period, that is t naught r naught plus r1 by 2r naught over 3 by 2. And you can substitute the values of t naught, and you will going to get the formula. T naught value is given 2 pi by q, and I think you will get the result like 2 pi by q, 2 pi epsilon naught m r naught plus r1 cube divided by 2 root 2 minus 1, and that's all. Thank you very much for watching.